All right, boys, in this problem, I want to give you a little bit of a harder related rates problem, more typical of an AP free response question. So I just kind of quickly summarized and created my own. But let's suppose we have a tank, right? And this tank is in the shape of a cone, right? So we have a conical, that means it's a cone. Let's assume it's a right cone. And water is leaking out at a rate of 4 cubic feet, so that means volume. Volume because it's cubic feet per unit of time second, right? When or if the radius, if the radius is 20 feet and the height of the cone is 30 feet, those are the original dimensions of the cone, what is the rate at which the water height, so the height of the water, is dropping when or at the moment when height is 10 feet, okay? So what I want to do is kind of go through the process of how I would think about solving this problem. The first thing I like to do is create a picture. So I'm going to draw a picture, right? I have a cone tank, like an ice cream cone, and the cone has 2 dimensions, radius, and here's the second dimension, height, right? And I happen to know that the radius of the cone, the original cone is 20 feet, so it's a big one. So the radius is 20, and the height of the original cone is 30. Okay? Now, what I also know is that water is leaking out, right? So there's a water level here, right? And it's leaking out. Maybe it's coming out that way, right? And so some things are changing, right? As the water level drops, both the radius and the height of the water level will be changing. Okay? So too, comma, will the volume of the cone. Okay, so we're losing volume, we're losing radius, and we're losing height as the water is leaking out of that conical tank. Okay? So now the next thing I want to do is I want to come up with a formula, right? And I want to come up with a boring, static, thousands of year old formula that describes the variables in this particular problem. And hopefully it's fairly obvious. If it's not, that's fine. But we are going to use the volume of a cone, right? And the volume of a cone is, if you don't remember, it's fine. The volume is going to be 1/3 of pi r squared, which is really the area of this circle, times the height. So there's the volume of a cone. Okay, that's the formula. Before I bring it to life and become a calculus magician by differentiating with respect to t, before I bring it to life, that's the boring formula that's going to describe the volume and radius and height of a cone. Okay? If you don't know those, you can just look them up. So, my next step is to say, okay, well, what do I know, right? Are there any constants? Because if there are any constants, then I can just plug them into this formula because they're not, by definition, changing. They don't need to be variables. However, because this is a cone, as the water level drops from, let's say, here to here, both the radius and the height of the water will be changing, and so too, therefore, will the volume of the cone. Everything's going to be dropping. So I can't plug in any constants now before I differentiate for radius or height or volume, because all 3 of those are changing and therefore must be represented as variables by definition of a variable. Okay, so now I'm on my next step. Now I'm going to differentiate everything with respect to t. And I'm going to take you down the wrong path first. Okay, not wrong, but I would say harder path. So if I differentiate with respect to t, I have to recognize there's a product rule in there to consider. Okay, so I'm going to say the derivative of the volume, in other words, the rate of change of the volume with respect to t, that's what I get when I differentiate v with respect to t, equals, now I have to differentiate this whole hot mess. And what I'm going to do is I'm going to pull out the pi over 3 constant and multiply by the product rule, right? Remember what I'm doing here, just to write what I'm doing, is I'm differentiating with respect to t, both sides of that boring geometry formula. Okay, I pull the 1/3 pi out. I'm going to product rule r squared, for which the derivative is not just 2r, it's 2r dr dt by the chain rule, times h plus r squared times the derivative of height with respect to time. Okay? This is my related rates equation, and it's quite complicated. And it's complicated because there are lots of rates and variables, in this case, lengths, that are involved. It's the rate of change of the volume. It's the rate of change of the radius. It's the rate of change of the height. And it also includes the radius and the height and the square of the radius at any moment. Okay? Now I'm going to propose an easier way to do this. Okay? And I'm going to erase all this and say, okay, maybe there's an easier way to do this. And there is. Okay? And I know that because I'm a calculus teacher. So I encourage you to think about this shortcut. Note that this problem is just asking me what is the rate of change of the height, right? So I'm looking for, my ultimate goal is to find dH dt when the water height is 10. So more information when, get my ugly mug out of the way, when h is 10. So just consider that, look, it's asking me a heck of a lot of information about terms that involve h's. I'm trying to find dH dt, that's the rate of change of the water height, when the water height is 10. So there's a lot of h's in there, and there's not a whole lot of information about r other than the original radius of the cone is 20. Okay? What I therefore am going to encourage you to consider is this. Okay? Although there are no constants in this problem, there is a constant ratio relative to the radius and height of the original cone, 20 to 3, 30, and the height of the water at any moment. And if you recall, because of similar triangles, that yellow triangle, or part of the yellow triangle, and the sparkly triangle are similar by angle. They both share this angle at the vertex of the cone. Angle, the 90-degree angle. So therefore, look, the radius to height ratio at any moment has to be equal to the original radius to height ratio. That's 2 to 3, or 20 to 30. Which really means that, look, 3r is the same as 2h. Or the radius at any moment is always going to be 2/3 the height. Okay? Now, given that, this is a nifty little trick. So I'm going to kind of rewrite that over here and get rid of this. At any moment, because of triangle similarity, the radius to the height of the water level has to be 20 over 3 of the original cone. That's because of similar triangles. Therefore, at any moment, the radius is always 2/3 the height. Okay? So watch what I can do. The radius and height aren't constant, but the radius is always 2/3 of the height. So what can I do with this little r here? Oh, I don't want to erase it. I want to highlight it. What can I do with that r? Still want to. With that little r here, I can replace it with 2/3 h. And then I won't have any r's in the original formula. So when I do that, I get 1/3 pi. I'll just call that pi over 3. R, which is 2/3 h squared, right? This is a not constant, but constant relationship between the radius and the height of the cone in this case, squared, because that radius is squared, times another height. Or when I clean that up, I'm going to get volume is pi over 3. When I square 2/3, I get 4/9. When I square h, I get h squared times another h cubed. Or, here it comes, volume ends up being 4 pi over 27 h cubed. Now that's nifty, because now this formula is a heck of a lot easier to work with when I derive with respect to t, and it's a heck of a lot easier to work with when I plug in values at the end, because I'll know all the values I need to plug in directly. They're given to me, and I'm not going to have to work for them. Okay? So now when I differentiate with respect to t, this formula, which is a lot easier than this formula, because it doesn't have 3 variables, it now only has 2. So I'm going to derive the left side with respect to time, derive the right side with respect to time. On the left, I get dV dt, that's the rate of change of the volume. And on the right side, I don't even have to use a product rule like I would have had if I had an r squared times h. I just derive h cubed, the 3 comes down. So 3, that cancels this 27, becomes 9. So I get 4 pi over 9 when the 3 comes down in front, times h squared by the power rule, times by the chain rule dh dt, because remember I'm differentiating with respect to t time and h ain't a t. Okay? Now I have a much easier related rates equation for which dv dt, that's the rate of change of the volume, and I know what that is. Okay, my last step when I plug and chug, oops, it says water is leaking out of a conical tank at this rate, 4 cubic feet per second. So what that means is that dv dt is not 4 but negative 4 because it's decreasing at that rate. I'm going to bring the 4 pi over 9. I know the height at this moment. Okay, it says when the height of the water is 10 feet. So I'm going to plug a 10 in for that height, which gets squared and becomes 100. And then I'm left with the dh dt, which is what I'm solving for. Right? This is asking me to solve for at what rate is the water height dropping. Right? That's dh dt, the rate of change of the height of the water. Okay, so now all I have to do is clean this up and solve for dh dt. Right? So I get a negative 4, that's 100, so that gives me 400 pi on top over 9 times dh dt. And again, to isolate that dh dt, I'm just going to multiply both sides by 9 over 400 pi. So I get dh dt, the rate of change of the height at this moment of the water in the cone, is going to be negative 4 times 9 over 400 pi, which when I simplify, shunk, that becomes a 100. So I end up with negative 9 over 100 pi. 100 pi is on the bottom. And because I'm looking at the rate of change of the height in this problem is measured in feet, right? Because volume is measured in cubic feet. Here's another feet for the height. So height is in feet per unit of time. dt in this case is seconds, right, up here in the problem. And that is my answer for the rate at which the height of the water is dropping in this cone at the moment when the height of the water is 10. Hope you enjoyed this. This is a little bit harder problem. We'll clear this up in school if you have any questions. Bye-bye.